Petroleum, right? Hear it all the time. So what is petroleum? That's kind of what we're hoping to explore through this video. Really, kind of why petroleum forms, what petroleum is, how it occurs geologically, and then in subsequent videos we'll talk about how we get it out, how it's used, and things like that. So you can see here, this is a picture of crude oil, and we talked about, especially in the last lecture and a few lectures before that, this idea of energy, right? So one of the things that makes oil famous is that there's an incredible amount of energy packed into this funky little fluid. You can see here in this picture, this is what we call crude oil as it comes out of the ground. And one thing that we'll explore during this sequence of videos is that crude oil is actually not very useful. It won't combust very effectively. It needs to be separated into its constituent parts, and then those are incredibly useful. We'll talk about that process a little bit later in a like I said, in a subsequent video. So when we think about energy, right, there's so much energy packed in this little fluid. So you can see 1 liter of gasoline. Think about a liter of Coca-Cola, right? A small plastic bottle. That contains about 9.7 kilowatt hours of energy. That's a joule, right? To kind of remind ourselves. So if you wanted to think about what that means for physical exertion, if you were to pedal a kind of standard bicycle at a fairly standard rate of speed, 13 to 15 miles an hour, you need after about 30 hours of pedaling continuously, you would have generated, or 3 kilowatt hours, excuse me. So the amount of energy in that little soda bottle would be equivalent to close to 100 hours of pedaling that bicycle, which is crazy, right? There's so much energy in this little thing. So collectively, we refer to oil as a hydrocarbon. That should make you think of the periodic table of elements rather than water, right? A lot of people think hydrocarbon, carbon that's a fluid. That's not the right way to think about it. Hydrocarbon means hydrogen and carbon atoms together. Another thing that's carbon and hydrogen atoms that you hear about often are carbohydrates, right? It's chemically very, very similar. So oil, which is what this is going to focus on, forms from a very specific type of organism. So if we think about plants, right? So wood, right? You can see here some beautifully stacked cordwood. Wood is primarily made out of a compound called cellulose. And cellulose, just a generic chemical formula for cellulose. So here you can see this is absolutely generic formula, but 6 parts carbon, 10 parts hydrogen, 6 parts oxygen, and then repeated n times, right, for lots of different types of cellulose. So one of the things that happens in this case is to produce hydrocarbons, we really need hydrogen and carbon. Oxygen it's the social butterfly of the periodic table of elements. And so in this case, oxygen will actually bond with the hydrogen, causing what we call oxidation of the hydrogen, and it won't be able to form long-chain hydrocarbons, which are just carbon and hydrogen. So just some common things here. Cotton, right? We grow cotton. It's famous because it has a high percentage of cellulose. So we use those fibers to make clothing, right? So 90% of a cotton plant is cellulose, at least the bud part that we extract. Wood or woody plants, right? So I showed some cordwood earlier, but here you can see this is a forest of ferns and brush and kind of other woody debris, even weeds and lots of stuff like that. High percentage of cellulose. Wood is roughly 45% cellulose. So again, high percentage of oxygen. Something like hemp, which has actually been in the news a lot lately, particularly for its uses, right? So hemp has about just shy of 60% cellulose. So it actually has more fibery material in it than kind of traditional wood. And in each of those cases, if those materials with lots of cellulose break down, the hydrogen will oxidize and it won't form hydrocarbons, right? Long chain hydrocarbons is what we're looking for. So we need a different set of ingredients. And generally, we need ingredients that are fatty. It's easy to think about animals, right? Animals are full of fat. Sorry, that's just the way that it is. Maybe some of us have a little bit more than we had hoped, but so it goes, right? So we're going to think about zooplankton, right? These little critters that live in the ocean. And if I were to draw a nice beach scene here, beautiful day at the beach. So this is where we're going to start thinking about zooplankton. And remember, it's something that's considered plankton. All that means is that it can't swim under its own power. So if an organism is floating around in the ocean, we consider it plankton, as opposed to nekton. Nekton's a fish that can swim. So there's no such thing as a plankton. It's not a type of organism. It's just a description of how they move around in the ocean. So if you can't swim, if you're just at the whim of the oceanic current, you're considered plankton. And we generally have plant-based plankton, which is phytoplankton, and animal-based plankton, which is called zooplankton. And so here we're going to think about zooplankton, but plants are also included in this. So you can actually see, here's an image of a couple of examples. There's lots of different kinds. You can see here a few different images of general types of zooplankton. But either way, we can think about them as little tiny critters. And those little tiny critters live in the ocean. Well, at least as far as this example goes, they live in the ocean. So animals, or in this case we're using zooplankton, generally have a very high percentage of fatty acids or carbohydrates. So a very common one that we see is palmitic acid, which is basically the precursor to palm oil. So it occurs actually both in plants and animals. This isn't exactly palm oil, but you can see here omega-3 fatty acids. People talk about these all the time for their health benefits, but they're just different versions of oils. And so notice it's not exclusively just animals here. It's both plants and animals. So it can come from both sources. But palm oil or palmitic acid, when we look at its chemical formula, and remember, zooplankton can be up to about 40% palmitic acid. So you should notice something quite a bit different here. In this case, C16H32O2. And so now the ratio of oxygen is much, much, much lower. And as this thing kind of undergoes some chemical changes, there's really not much oxygen in there to kind of suck up all of that hydrogen. So I'm going to draw the molecular formula here of palmitic acid, and hopefully you can see what I'm talking about. My wrist is tired, right? Drawing all those hydrogens. So here, again, palmitic acid, palm oil, mostly carbons and hydrogens, and then these hydroxide molecules kind of packed onto the end. So as this thing undergoes some sort of chemical change, the oxygen really is not a key player here, as in the case of cellulose. So here, we're going to see something that is primarily carbon and hydrogen. And remember, that's what we're after, right? Hydrocarbons. All right. Well, I slightly modified my basin here. I made it a little bit deeper just to prove a point. So now how does this all work? Well, these critters, these zooplankton and algae, they live in the photic zone up near the surface where there's lots of sunlight, and the phytoplankton and algae can photosynthesize. The zooplankton can eat those, so there's a lot of life up here. But everything dies, right? That's the sad reality of existing, right? So when these critters die, they settle down to the bottom. And it's actually what we call the organic flux, right? So again, flux is really just a fancy word that means flow. So the organic material, in this case I've labeled that OM, fluxes down to the bottom and piles up on the floor of this basin. Now, the other thing that we need to think about, and I'm going to use a different color, is the sedimentary, or the kind of the rock material that's brought into this environment. So here I've added a couple of other colors, little particles, and also that flux, right? So that would be what we would consider the sedimentary, or the kind of the sediment flux versus the organic flux.